take some questions and yeah, I'll try and answer to the best of my ability. So Mark, just testing, you can see my screen? All good?
Yes, all good.
Okay, thanks. Okay, so what we're looking at is we're looking at the VRV IV Plus. We've had it released to the market for about, I think, approximately one and a half years now into our market. So it's just a refresher for some of the people that haven't or haven't been exposed or haven't been showed the technology. And at the second part of the presentation, I'll be looking at the hidden VRV, which is a condenserless system. I know most people probably, when they heard of it, they thought that thermodynamically, how could this be possible, or practically, how could this be possible? We will explain the innovation on how the Daikin R&D has actually made this work, especially for our industry. And then lastly, I'm just going to touch on a 2-minute with the Daikin air sensor that we have available or possibly available in the next year or 6 months or so. So my name is Nishal Rana. I'm the consulting sales engineer for Durban KZN. So let's kick off the presentation. So looking at the background of VRVs, around October 2012, we've come up with the 4th generation of VRV, which is our VRV IV, and we've now moved on to the VRV IV Plus. I'll explain later on in the slides what's come about with these changes. So in the end of 2018 or so, that's when they started the R&D process and got them into full swing production. And in South Africa, we brought them in around the end of 2019. So what Daikin also looked at, which was the end of 2020, which was last year, we released it internally. Some of the data for the VRV5, which is what we call the blue evolution. It's no secret to most of you that are in the training that Daikin's Sky Air range and Split Air range, we've gone completely R32 because of the global warming potentials and the pressurization from the initial Montreal protocols. So Daikin's basically looking at R32. When R410 first came out, everybody was hesitant. We were the first ones to come out with R410. Nobody wanted to make the change from R22. Nowadays, R22 is a swear word, or should be a swear word to most people in the air conditioning practice, and R410 is the acceptable standard. In the next 3 to 4 years, R32 is going to be the acceptable standard. So rather make the change now than later. So the discussions about R32 and its benefits, that's a topic for different discussion. But in a nutshell, it's more efficient. It uses less charge, and it's more ecologically friendly. So back to an air conditioning system. So most people do know that the compressor, or the outdoor unit, as most people call it, is the heart of any air conditioning system. And that's where the most energy is used, right? So what would obviously impact the efficiency? It's number one, the fan. So it's the fan, it's the heat exchanger, it's the refrigerant that's used, and it's the actual compressor. Hi guys, when you join, please can I ask that mics be put on silent, please? Thank you. The controls and you also get heat recovery, and obviously maintenance and the installation, which impacts on the efficiency. But let's presume that the maintenance and installation is too standard, and let's look at the components of what actually affects the efficiency. So let's look at the heat exchanger, right? So the heat exchanger, let's think about what a heat exchanger actually is, right? So for how to increase efficiency on a heat exchanger. So the heat exchangers are obviously designed to maximize the surface area between the two fluids, right? And create obviously a turbulent flow. So while minimizing the resistance to the fluid flow through the heat exchanger. So everybody understand that. So the smooth surface also on the actual heat exchanger allows for a lower pressure drop. So also allows, so think about it. So you've got a smoother surface and you've got a rough surface. A smooth surface allows for less pressure loss, so it allows air to flow through easier, right, to condense. And a rougher surface would obviously create more resistance or turbulence and create a higher pressure drop. So it makes, so why do we need to have a low pressure drop? We have a low pressure drop so our fans don't have to work as much, or our compressor does not have to work as much, because your main target is to achieve efficiency, right? And the heat exchanger's performance can also be affected by the additions of fins or corrugations in one or both directions, right? So the increased surface area also may channel the fluid flow or induce turbulence. So heat exchanger of what's in our VRV4 Plus. So obviously we've got our we've got the four-side heat exchanger. That's 1, 2, 3, and 4, right? So maximum surface area would obviously give you a better heat transfer, or a footprint for heat transfer. You've got 3 rows of the heat exchanger itself. That's where your copper tubes runs through and joins in with your fins. You've got a reduced fan pitch. So the reduced fan pitch, why? So obviously you want to the maximum, the more surface area you have of a cooled component, when the warm ambient air passes through it, it also gives a better efficiency or a better heat transfer, because this is what we're trying to achieve here, right? So basically, that's what we've done in terms of our heat exchanger to increase the efficiency. So obviously, our R&D team looks at our competitors, what they do, because Daikin has invented VRV, hence VRV is patented into Daikin, and other people are called VRF. So let's look at a typical competitor. So just taking a normal 10 HP system, which is approximately 28 kilowatts, if I'm not mistaken, of cooling, and looking at it comprised into a system. Some of you guys who are familiar with VRV do know what this system line diagram looks like. And taking a competitor's machine to do the same duty, to do the same run, Daikin did a comparison, and our competitors use more charge. Now, how are they achieving higher efficiencies than us when competitors' surface area of the coil is less, and on top of that, they're using more charge? There are ways to do it thermodynamically. You could go with very thin material to increase the heat transfer rate, but that's a story for a different day. This is just explaining the case study. So even in a case study 2, for a 20 horsepower system, we also note that our competitors are 19% higher, or we are 19% lower in charge than the competitors. So obviously the less refrigerant volume is required by adopting smaller piping of diameter 7 millimeters is what we used, right? And we have an average about a 20% difference with the competitor for the heat pump of the VR4 outdoor units. So looking at the compressor itself, just get this. So looking at the compressor itself, right? So the compressor, if you look at H1 to H2 on the enthalpy, that's that work there, and that is equivalent to the diagram for this work here. And 0.2 and 0.3 will also be that work there for everybody to understand. We note that on the compressor, the total energy used by the compressor is obviously quite low, and we are looking at, just do this very quickly, give me a second. So how do you look at EERs? So look at EERs with the cooling output, which is H1 to H4, right? That's that portion there. That's the cooling output, right? Relative to or divided by the total energy input. So that is your energy input. That is your work done. And the lower work or the less work you would do from H1 to H2, the higher your EER is going to be, because it's obviously divided by that number. So let's say, for example, your cooling output was 3 and your total energy input was 1, you would have a EER of 3. So what are we trying to say? We're trying to say that our compressor is highly efficient, and I'll show you why in the slides to come. So our compressor is highly efficient, therefore giving you the best possible EER. So we have our scroll compressors with a hermetic. They consist of 2 scrolls, which is one fixed, one orbiting, and the discharge ports at the center. So I'll show you a more detailed diagram of this now. So what's the pros? Obviously you can achieve a high EER, also at part load, because our compressors are fully inverter. The low noise levels. Many people who's installed a Daikin or has a Daikin or specified a Daikin, they know that our noise levels are the best. There's low or no maintenance. It's no secret in the industry that our compressors give you at least minimum 5 to 10 years minimum with no issues, and it's cost effective in the maintainable cost and the life cycle cost of the equipment. So how have we increased this efficiency? So we've gone with 50% thinner on here on the compressor blade, on the scroll blade, sorry, and that is realized by adopting new material. So we've got new material, which is Thixo casting process, which is the iron-based alloy, and it's a way to cast a material in a semi-molten state capable of producing very high strength products. So what that means is that you can go thinner on the material, right? But you're not compromising on the strength and on the quality. But what you are also achieving by going thinner, you're achieving a higher efficiency, and that's what we've done. So if you look at overall, we've come up with a 2% more efficient compressor. So in terms of the density of the compressor's oil, that's also important to prevent compressor problems. Obviously, if you've got a very thick, sludgy oil, you're gonna run into issues sooner than later. If the compressor oil is also mixed with refrigerant or contaminated, or has gone acidic, the viscosity does become low and increase the chance for the compressor burning out, right? So the lubrication of the compressor is not, that's what happens when the lubrication is not sufficient. So what do you need to do? You need to have oil density checks. Methods must be more strict. You probably do it, call me a liar, but maybe every 6 months or every year, or a major service. So it's also accurate evaluation of the oil dilution by means of a new oil dilution sensor, right? So these are the kind of things that needs to be done, and we've got these oil viscosity sensors now that's also put into our new VRV IV+. So what does that mean? By changing oil, by doing preventative maintenance, you can reduce the failure rate of compressors by 30%. So the new compressor that's developed for the IV+. So the intermediate pressure adjustment port allows a small flow of refrigerant from high pressure side to low pressure side in order to guarantee that the movable scroll remains fixed and fixed against the fixed scroll and ensuring that there is no leak, right? So it's all about looking at the power to work to time ratio. Your amount of power that you are going to consume in terms of mechanical, which is inversely proportional to the electrical power, right? you got to look at the amount of work done. The more work you are doing, the more power you're going to consume. That's the thermodynamic laws or mechanical laws. So what you want to do is you actually want to reduce doing unnecessary work. So with back pressure control, we want to guarantee that the movable screw does not allow leakage, right, from the high pressure side to the low pressure side. Because what's the point going through the compression cycle and then leaking it back into the system? It doesn't make sense. You're doing work for no reason. So by what we've done with the back pressure control, we've also increased the efficiency of the system. Just a quick video for you guys to have a look at to visualize. Okay, so as I was saying, that was the previous slides that we looked at. We're looking at all the different components that has been adjusted or amended or modified to achieve better efficiency. So now let's look at the DC motor, which is a digitally commutated motor, right, that we have, and what the change is. So we've got Dye can improve the system by using neodymium magnets, right? These magnets are about 8 to 10 times better than the normal ferrite ones that we have. This is also shown on the picture with the bullets, right? You'll see the bullets now, and they are slim and very small. And by putting them on a more easier to curve iron, you induce a second magnetic couple, which is a very strong couple due to the fact that the neodymium magnets have a very strong magnetic field. And by using the easier curved iron, the reluctance will be reduced a lot. So what does that mean? It means that there's no time delay or less time delay, right? Because it reacts quicker, right? And also you got to think when you have startup. So what's the worst thing? You've got power failure, or you've got a large commercial building, you've got a power failure, and your machines take, your old non-inverter machines used to take what, sometimes 15 minutes for a compressor to allow it to start up again. So what this allows it to start up rapidly again. So I might be incorrect on the or I might not be 100% confident on the time factor, but I think it's 120 seconds before the machine can start up again. So just to visualize it, that's what we're talking about. So by having the neodymium magnets, we induce a permanent or a stronger magnetic field. So that's the benefits of the DC motor by having the stronger magnetic field, and it's AC driven. So let's go to this DC motor. Give me a second. So essentially, from the stator pole to stator pole, so the DC magnets, that's a second magnetic field that I spoke about that's been induced in it, and it allows the rotation to be much smoother and with less resistance. Efficiency wise, so the efficiency of the DC or the digitally commutated motor is obviously much higher, right? So it's 40% higher at around the rotational speeds of around 600 to 500 RPM. And as you go higher in the RPM, that's like maybe like a very hot day where the motor needs to do more work. you're looking at about a 20% higher than what we currently have on full load. So the advantages of the ODM is that you obviously have a large torque with the same electromagnetic force, right? Looking at the conventional motor, right, with the inner part to the ODM for the outer part, and there's over 50 fan steps, and the previous generation had 10. Right? So what does that mean? Because you've got more steps, you've got a more stable rotation, and you have better volumetric efficiency. And when they do all the calculations, they sum it up to an average of about a 3% better fan motor efficiency. So now that's where you're going to start thinking and think of all the stuff that I've spoken about so far about how many different changes we've done and how it's affected the efficiencies. And that's why our product, in our opinion, and by fact and proof of the pudding, is the best in the market in terms of energy efficiencies. So the inverter control, also known as the VFD, which is a variable frequency drive. And what is the main goal of it? Is to adapt the auto unit to the requested load. That's what the inverter is. So before, when we had non-inverter technology 30 years ago, you either had bang on, bang off. So you had maybe two compressors. So you had 100% capacity, 50%, and you had 0%. Obviously, when it switched off. You could have had a two-stage compressor. Maybe you'd have had 4 points. But with the VFD, obviously you can accurately control how much of duty or how much of work you need to have done for the exact point. So you could be, for example, at a 55% load, and then your next load could be at 77% load. With the variable frequency drive, your tolerance factor is maybe about 1% or 2%, and you get exactly the amount of duty that you need. And obviously, the main purpose is obviously to have inverter control is to save on energy and obviously improve on the comfort. Because what's the worst thing sitting under a cassette unit or a diffuser is that all of a sudden the expansion valve opens and you get a dump of cold air into your coil and you freeze because you probably have air hitting you at about 14, 15 degrees and it becomes very uncomfortable. So the inverter control, what it does is it opens the expansion, it will allow certain refrigerant to pass through, and the expansion valve will open incrementally to allow for certain amount of refrigerant to come in. Basically looking at the change of the control speed. In a control way, that's how they do it. They adjust, when you adjust the frequency, you can adjust the amount of RPMs that speeds that. So obviously the lower the frequency, the lower the RPM. So the need for a device is obviously to change power in a controlled AC wave. So with the Daikin system, inverter system, right? So it's the easiest way to change a frequency. So what we do is we have your input, your alternating current that comes in, right? That's your main power supply. We've got a converter, right? That converts the AC to DC, right? And then converts it again to AC. Now, some people might be a bit confused with this, so I'm going to say this again. You got your power supply that comes in, your three-phase power supply, right? We convert it. We convert the AC to DC to get a clear line voltage with no fluctuations, right? And then we convert it to Daikin AC again. Why do we do that? Because can you see the difference between the input and can you see the difference between the output? The output is a more straight line, clear, more stable voltage. So the wide ranges on the non-step inverter control. So we look at the steady operation of it. So you got the feed forward control for the VRV IV and quick convergence of the target and reduction of waste or compressor operation. So I spoke about this before. You got quick action. You got various methods of trying to minimize the amount of work being done, which obviously directs your amount of power supply being wasted. That's basically the capacities. So nothing's changed in terms of our older models. So our older models was called the RXYQ, whether it was a 8, 10, 12 or whatever, it was RXYQ, the number, which is a 8, 10, 12, and T. Now we just call it the same number. It's called the RXYQ, 8, 10 or 12 or 14, U. So it's just changed from a T at the end to a U. Physically, not physically, capacity-wise, no change in terms of the capacity. The compressors are the same. The capacity control ratio has just been adjusted a bit to have better benefit in terms of control. But essentially, you can still do a maximum of 318s together. And the reason we do 318s together and we stick to 318s together, it's because of the gas laws that's allowed in international standards, but in particular to Europe. As you guys know, our product comes from Europe. The reason is because you got a certain amount of charge that's allowed in a system. And when you're designing, like, let's say, for example, a hotel or an office block, and let's say you have a machine in a storeroom or a room, how it works is that the amount of charge in your total system must not exceed a percentage of the volume. I think it's 400 grams per square, if I'm not mistaken, in the room area. Oh, sorry, 400 grams per cubic meter, sorry, in the area. So what that means is that if you had a leak in a hotel room, you don't want to asphyxiate the person, right? By removing all the oxygen from the room and killing the person, because it's so quick, you can't smell the refrigerant. It happens within 10 to 15 seconds, even quicker in some cases. So that's why we still do a maximum of 318s together. So our joining has not changed, where we can put 320s together. It's still 318s. So a maximum of 54 HP per system, which is 150 kilowatts. So also we have the refrigerant cooling. We've also had that on our VRV IV. So the efficiency of the heat exchanger is also increased around 5% because of the airflow pressure loss that I explained earlier. And the reliability of the electrical components is also increased. Now, the refrigerant temperature is at least always 5K or 5 degrees below the air temperature. And the propeller cooling for the inverter power module can be offered even if the installation space between the outdoors is tight. So what we've done is looking at our competitor and looking at us, our cooling efficiency increases about 1.7 times. Our heat exchanger efficiency goes by 5% up. Our lower failure rate thanks to the proper cooling. And if you look at our electronics, well, majority of the time, why do electronics fail? Think about these machines, right? These machines are sitting outside on a roof or on a floor area or wherever the case may be. It's absorbing direct sunlight. It's absorbing high humid air. Obviously, these electronics do take a knock. So electronics like to be kept cool. They like to be kept around 25, maybe to 26 degrees. That's sort of what it likes to be at, or what it can be at as a maximum range. Think of your server rooms. Why do you cool a server room? Because you want to cool the electronics. They give off heat. So what Daikin's done, and we've done it before, but we've just increased the efficiency of it. We provide a cooling circuit to our electronic boards to make sure that the electronics are always cool. VRT, we've had VRT on our VRV IV also, right? So VRT basically is your variable refrigerant temperature. So let's say, for example, a high load is required on the startup. and most of the time operation is on part load. So what I mean is that 8 o'clock in the morning, your office opens. For those people who come to work on time, everybody walks into work at 8 o'clock. The aircon is doing its maximum duty because now it's trying to cool down, number one, the structure. Number two is trying to cool down or trying to remove the heat of the people load that's entered the building. So that's what this means. That means a high load is on startup, and during the day, when the office is now being cooled and people are going for lunch, or people are moving from one open plan office to the canteen or the boardroom or whatever the case may be, right? The point is that the loads vary. What the VRT does, the VRT actually increases the refrigerant temperature automatically. So how does increasing the refrigerant temperature help? It helps, number one, because you don't end up overcooling the space. Number two, you use less work to make 6-degree refrigerant as opposed to 11-degree refrigerant temperature. That's basically your VRT, explaining on a graph that at 35 degrees is what the unit's designed to do. That's going to be at almost 100% of the load. And then as the temperature drops during the day, let's say it drops to about 30 degrees, you can see you are maybe at about what, 75 or 70% efficiency. You have changes on the system, because if the evaporation temperature is fixed, think about it, right? You're going to excessively cool it. You're going to get that dump of cold air into the space. When you walk in, you're going to have your aircon set at, sometimes you find it, you have your aircon set at 23, but it feels like it's 20 degrees in the office. You get cold feet. This is all a result of overcooling. And again, I'm going to emphasize, what is the problem with overcooling? It is a waste of energy. And this is the whole thing, that what we've come about, and the whole purpose of the presentation, and the whole purpose of change. The whole purpose of change and new models is to always improve your energy efficiency. So the details of the VRT function, yeah, you can go up to 6 to 16 degrees. That's on the floating weather dependent. So to gain the maximum energy efficiency, it is also required that the units are always adapting or evaporating or condensing temperature to optimize a balance point. Generally on our VRVs, 50% of the building load is actually its sort of sweet spot where you gain your maximum efficiency. So that's a temperature control. So how does it actually, the application possible. So how does it actually act or react, let's call it, to it. So where there's a quick increase in load and it's expected, such as like a conference room, as I explained, you've got a load moving from one area to another area. So now the conference room becomes needs a high startup refrigerant temperature. A low refrigerant temperature in order to cool the room quickly. And now the offices don't need any cooling. So what will happen? Maybe the expansion valve will close off in the office if it's met temperature, or it will be open maybe 5% or 2% or 3%, whatever the need may be. And then the conference area will open at 100%, but it doesn't just open bang 100%. Because of VRT, it opens slowly, so it'll open incrementally, so you still achieve your comfort, because it's a worse feeling to cool a room down immediately because it becomes uncomfortable. Then also you give the customer a choice for fixing the coil temperature, which should avoid cold draft. So as I explained earlier, so let's say, for example, the customers have an office full of people who prefer it to be warmer, but maybe they don't like, maybe they still want to eliminate the humidity. You could change your evaporation temperature from 6 degrees to possibly 9 degrees, if that's what suits them. The fact of the matter is that the flexibility is there. Also, think about like a diffuser. Let's say the architect hit the stuff up, or you put you put wall grills at maybe 2 meters after the finished floor level, and now the person at the desk is now starting to feel uncomfortable. And let's say everyone's feeling uncomfortable. You don't have to have the VRV discharging it having an evaporation temperature of 6 degrees. You can do it at 9 degrees. trust me, 3 degrees makes a big difference in terms of comfort. You can try it. That's why people are comfortable at 23 degrees and are uncomfortable or start getting twitches or start getting a bit jumpy at 20 degrees. Oh, sorry, I didn't touch on one more thing. Also, for the temperatures also can be used in for computer rooms. So computer rooms have a high sensible load with a very low latent load. So what you actually want to do, you actually want to raise the evaporation temperature of the server room, because there's no latent component to or there's no humidity or such in the room to be removed. So you can go a little bit warmer on the refrigerant temperature to still achieve the correct end result without the compressors cycling on and off and tripping. This is just a mild case study that was done. Basically, the essence of this, of what I want to explain, is that you've got older units. You can see you've got all the older units. So let's say, for example, you've got an old R410A system, right, which is the T series or the P series, right? You could replace the condenser in a case of failure. So let's say you have a client and your client calls you and says, hey, Mr. Consultant, I need you to come and have a look. Or hey, Mr. Contractor, I need you to come and have a look. I have a problem. My air conditioning's down. No problem. You go to him, you have a look at the thing, and let's say the compressor is corroded or the compressor is burnt out and it's 15 years later. Not a problem. Your customer or your end user does not need to go and change his entire indoor arrangement with the piping, everything. You can leave all of that the same. You obviously got to flush the line. You've got to do your pressure test. You've got to make sure that all the indoors are still in good working order. You've got to make sure that the electrics are all still intact, and all of those things are still in operation. And you plug in a new condenser and you connect up, and Bob's your uncle. There's no problem at all. So essentially, that's what you can do with these units. They are backward compatible. But be careful. If you have 3 condensers on one system, you cannot replace. If they're on one system, so one system meaning that 1, 2, and 3 condensers go into the same pipe run. You cannot change one condenser and leave the other 2. Or you cannot change 2 condensers and leave the other one. You have to change all if they are on the same system. Right? I hope everybody understands that. If they are individual, so let's say this condenser serves that block there, and let's say that condenser serves that block there, it's fine. If they both have failed, you can replace this, or if one's failed, you can just replace this and leave this, as long as they are not connected onto the same pipe run. You can obviously still add our ITM, our INET to kilowatt meters, etc. onto this. So the VRV, so this is a comparison between the VRV 4 Plus and the VRV 2, basically looking at the efficiencies. So an average cooling efficiency, remember VRV 2 was non-inverter, or I think it had 1 inverter compressor and 1 non-inverter compressor. And you look at the average cooling increase of 60%, thanks to VRT. Because remember now, before, it didn't have any variable refrigerant temperature, it didn't have that technology. So obviously the efficiencies weren't there. So you look at an average of a minimum of 60% better efficiency from your older VRV to your newer VRV. So you could even get a call from your customer saying, hey, I've got this old VRV system, flip, it works like a bomb, but yes, the energy bill's crazy on this thing. You can tell him, no problem, Mr. End User. We've got a solution for you. The VRV condensers are backward compatible. The condensers uses more than 80 to 90% of the total system's energy. If we change this, we can achieve an estimate of about 60% reduction in your electrical consumption. So it's all about knowing what the product can actually do in your application, because you never know when you do meet an end user what the outcome or the requirement may be. So the VRV configurator, basically you got to customize settings. It's very similar to the VRV4, and respond to your customers' needs. All the installers can now do is just set up a PC, or we have our Bluetooth tool like the service checker that you could have a look at, and you connect in. You've got a transmission box. You look at the competitors. Sorry, the competitors have a transmission box, and also we've got a digital display on ours where they are still looking at using dip switch. That's what our digital display looks like. You'll get an error if there's an error. Touch wood, there's nothing, but if there's an error, you get an error code which can be directly checked. We have an app. You can check it to the app, or you can give our techies a call, and they're more than happy to assist you guys. And yeah, you can obviously do your fault finding and figure out why a certain thing has happened. So summary of the thing, we basically got a 4-side 3-row heat exchanger, which has increased our efficiency by up to 40%. High strength scroll compressor, which has given us a 2% extra efficiency, right? Your ODM motor, fan motor efficiency, 3%. Your refrigerant cooling of the inverter module, right? It's 1.7 times better, which increases the heat exchange efficiency by about 5%. The wide range of the non-step inverter control, right? Your compressor cooling capacity plus 5% against a standard inverter control. Your VRT, which is about 30% more efficient than non-VRT systems. Bearing in mind, it doesn't mean it's 30% more efficient than the VRV4. It's the same in terms of this category because the VRV4 has also VRT on it. We are comparing this to non-VRT systems, which is your VRV2. Phase change material of the material tank and the continuous heating, which I don't even touch on because we very rarely look at the heating factors. So thanks for that. I'll take some questions now, or Mark, you prefer me continue with the hidden VRV and then look at the end? Mark?
Yes, I'm here.
I'll take questions now or take it at the end. I'll do the hidden VRV now.
Yeah, do the hidden VRV now, then the guys can ask questions afterwards. Thanks.
Sure. Thanks. Okay, cool. So I know most people were looking at or were more interested in looking at the hidden VRV for city centers. So as I explained earlier in when the presentation started, that we've come up with a hidden VRV that has no condenser on the outside. It's not magic. It's not voodoo. It's just engineering. And I'm sure most of you guys will be impressed with the technology at the end of this presentation. So, can an auto be invisible? Yes, it can. So what's one of the challenges when installing an HVAC system? You have all of the rigging to go into place. I'm sure at least every contractor has at least once had an incident where a condenser unit has dropped or an indoor unit has dropped. If you haven't, you guys are very good. But I'm sure everybody has experienced it or seen it or felt it at some point in their life. So that's a challenge. The challenge is rigging, right, and transport. And the other challenge is actually getting an outdoor space. So, if you look at common hurdles that we have in the building industry, it's you're right. You got in South Africa, we have something called a MAFA, and basically buildings that are more than 60 years old need to go through special architectural clearance and etc. to try and get alterations done or to put a condenser on the roof area or to build a slab on the outside. Because facades are quite critical to the architects and the MAFA consultants. So what we've looked at is when you're looking at an aircon system is to have something installed at the shop front entry. So what we can do is let me just get to it. Sorry, makes it a bit easier. So what's the typical condenser that you look at? You got your heat exchanger, your fans, etc., your compressor, and you got your casing of the unit itself, right? So what we've done is, if you look at these two components, what
You're not seeing anything.
what we've oh, it is shared. Sorry about that, guys. I just heard that nothing was being shared. Mark, we all good now?
Yeah, that's better. And just show going to full screen mode.
Oh, crap. Sorry, man. Oh, I'm so sorry, guys.
So I think just do that enable editing and it will work to get it in full view. I think that's where you're getting stuck.
Is it not in full view anymore?
No, just showing the slides. If you say enable editing, it will allow you to go into your
Yeah.
presentation mode.
Correct. Click on enable editing.
Sure. Much better now?
That's it. Thanks.
Thanks. Okay, so sorry, guys. I'm just going to run through the silly questions again. About the common hurdles in HVAC. This is what I was talking about, the rigging. Sorry, I presume that you were seeing this. This is when I spoke about people have dropped units at some point in their life while rigging, and it's not an easy task. So the challenges, as I was talking about Amafa, you get these old buildings that you can't adjust the architecture on. And I stopped about the unique solution. So basically your components, what we've basically done is this becomes now the outdoor fan motor, which these fan motors would have normally discharged on the side. We've shrunk it and made it the same size as an indoor unit. And we've taken the compression module itself, right? And we've made it the size of a dishwasher. The indoor unit, if you want to call it, the indoor looking unit that was shrunk, which is normally the air discharge point, right, the air side of the condenser unit system. We've shrunk it so that it has an inlet and an outlet. So you have air from here blowing out, warm air blowing out. That would be here or here. And you have a cold air coming in. And basically you've got no condensers at all on the system. This here will have a refrigerant circuit that will run to the compressor module. The compressor module will then have a refrigerant circuit that will run to your indoor units like a normal VRV system. You'll see it better in the slides to come. So that's physically the size of what it looks like. So you can even hide this in a dresser, right? So the capacities we have, previously we had only a 14 kilowatt cooling capacity. We've now got a 22 kilowatt, which is equivalent to our 8 HP system. Hopefully in the future, we'll go up to a 10 and then a 12. What's good about this, it's easy to transport. They can fit in the back of a transport buggy. That's the size of the fan module, which is the size of an indoor unit, right? In corrosive areas, I will advise that this be corrosion treated, the indoor coil be corrosion treated, as you would normally do for full fresh air systems. The compressor module does not need a drain, and it makes less noise than a fridge. The air module, right, which you would connect your inlet and outlet louvers to, is only approximately 400 millimeters high, and it's designed for the silent operation. It's got a V-shaped heat exchanger, so better heat transfer. centrifugal fan, so it's obviously quiet, and the painted and perforated and insulated partition plate to prevent backspill of air. You got a standard filter on it. Be careful though, filters need to be cleaned. Remember, the dirtier your environment or where you're drawing in the new air from, the dirtier that filter will be. So you got high efficiency inverter fans on these. You can see up to 200% for the 5 HP and up to 191% for the 8 HP. So this diagram is a bit small. I'm gonna share a different. I'm gonna come back to this on a PDF. I've got a better looking presentation for that. External static, you're looking at about 60 pascals standard. So that should be more than enough to duct your air out, even with a dirty filter. And you can go a maximum of 150 pascals. So let's say, for example, this is where your storeroom was, and you wanted this unit to be housed there because of obviously maintenance and not to interfere in the normal working operation of your offices. You could increase that, and your consultant or your contractor will have to calculate that 150 pascal duct run to draw the air out. But also remember, the higher you're going to run your speed, the more noise you could generate. The compressor in the refrigerant module. Now, please, I need everybody to follow me on this. Your air module is the part that needs an intake and an outtake louver, and it does the same function as the condenser fan motor, right? By using air, it's the air circuit, and you get the compression module, right? Or the compressor module, which houses the compressor part of a normal outdoor unit, right? Easy access, simple to install, no drain needed, small footprint, non-welded bottom casing, so you're not going to get corrosion, right? Back and top refrigerant connection, so you could come in at the back of the unit, depending on your layout, or you could come in at the top, depending on whether you want to put this higher on like a cantilever bracket or whatever the case may be. So the pipe runs are quite decent. So from the air module, you can go up to 30 meters to the compression module. And from the compression module, being a 22 kilowatt system, you can go another 70 meters maximum to your last outdoor. Other unique features, you can connect it to an AHU. We don't unfortunately bring the air curtains. Sorry, I should have removed that. And your fully inverter VRV range. So you can connect it to a very small AHU if you had to, right? And you can connect it to our normal VRV range that you would normally use. And it also uses the VRT technology on it that I explained earlier. It also connects to the same software for the VRV configurator, so no problems there. So we've taken the concept one step further. This is done somewhere overseas. I don't know, most of you guys have seen, you get the industrial looking shops, like coffee shops and stuff, right? So you can also insulate the ductwork, right? You can insulate the sound sensitive areas, and the sound comfort's also key. The worst thing in a restaurant is having this buzzing noise for the indoor fan motor, because remember now, the fan side or the air side of the circuit can still generate a lot of noise depending on what speeds you're running at, right? Because it's inverter, it'll obviously aim to always run at a 50% or 40% speed, but it does go up to that 100 or 120% speed in the case of like a very warm day where the ambient air coming in is quite warm. So we have taken this concept one step further with 5 new sound reduction steps available, right? You can adjust the low configuration on the display, on the LCD display, right? But for everything that you do, there's a sacrifice. If you're going to reduce the sound to step 5, which is going to be the lowest sound, you're going to get an 18% drop in your cooling capacity for 9 decibels, which is quite decent. Depending, I mean, you could have a scenario where you don't need 22 kilowatts, where you only need 18 kilowatts. Then this is fine. You can reduce the capacity factor by it, because remember, the noise, the low noise operation can be easily set up in the compressor module. It's just a matter of clicking a few buttons to adjust it. And the only problem is, as I explained again, is the functionality of it. So to reduce it by 9.5 dBAs, you're going to lose 18% of your capacity. Thanks everyone for your time. I just want to go to I'm just going to show you guys 2 more things and I will be done.